All right, so with this problem, we're going to find the area of the region that lies inside the first curve and outside of the second curve. I'm going to be doing number 27. So first, we want to make a pretty big graph. Maybe we need a lot of space for this one. And I'm going to try to make something that just a few units, just maybe like 4, just to stay consistent. Okay, so we have to try to find these areas between these curves. R equals 3 cosine theta. This is one of the graphs that's pretty easy to draw, to sketch, because cosine theta is just a circle when you have it like this. That 3 just tells that we're going to move 3 units to the right and then start our circle. So we're going to go 1, 2, 3 right here. And we're just going to draw a circle that goes in back and touches origin. It's going to be a straight circle like this. If it was a negative 3 cosine theta, all that means that we go 1, 2, 3 and we would start right here. And the circle will be like this. If it was 3 sine theta, that means we would go up to 3 and make a circle like this. And if it was negative 3 sine theta, it would go down 3 and be a circle like this. So these are probably the easiest polar graphs to draw. Now, the second one we have to draw is r equals 1 plus cosine theta. This is the one that we have to focus on. So let's make a table. And I want to make our x value, or our input, right? Because we're not really working with x and y anymore. Our input is going to be theta, and I want our output to be r. So I'll make a pretty big one. Now, I also want to, on our graph, we want to draw our important angles, right? Just make note of it. So we know that right here is angle is 0, right? These are going to be our inputs. So our angle is 0 right there. Our angle over here is pi over 2. Our angle over here is pi. Our angle over here is 3 pi over 2. And then I want to draw some important angles just in the first quadrant. So we know something like this, right? Remember, it's just a sketch. It doesn't have to be perfect, but this is going to be pi over 6. Now, over here, kind of in the middle, this is going to be our pi over 4. And then if you go up to about 60 degrees, this is going to be our pi over 3. Now, I want to start by plugging in 0. I want to see what happens at theta equals 0. So at 0, we can work on the side and let's see. R equals 1 plus cosine of 0. So this gives us r equals 1 plus, cosine of 0 is 1. This is 1. So r is going to be equal to 2. That means that angle 0, right? So remember, everything we do when we talk about angles, we're going to kind of be like in a sweeping motion, right? We're kind of going along the unit circle. So at 0, at this angle, we're facing the angle 0. When we face angle 0, we're going to land at 2. So we're going to make a point right at 2. Now, I want to know what happens at pi over 2. I just want to see, kind of get a rough graph. So at pi over 2, let's see. So r equals 1 plus cosine of pi over 2. Cosine of pi over 2 is 0, so we get r equals 1. 1 right here. That means that we don't know what happens here yet. We don't know. But we know that once we sweep over to pi over 2, we're going to land at 1, right? So when we're facing that angle, when you're facing pi over 2, you're facing an angle, you're going to go up 1 unit towards that angle. So we're going to make a point right here. Next thing that I want to know is what happens at pi. So at pi, we get r equals 1 plus cosine of pi. And this is 1 plus, and then cosine of pi is negative 1. So we get r equals 0. That means now, when we sweep over to pi, and we're facing pi now, right? Put yourself kind of in that angle and face that angle. You're going to go up 0 units. So we're actually going to be right there. Be right here. Now, you could probably guess and do this fast by now on this next quadrant angle, but 3 pi over 2, if you do the math, you get r equals 1 plus cosine of 3 pi over 2. It's the same as cosine pi over 2, so we're just going to get r equals 1. Right, so it's kind of symmetrical when you get to here. So you have a point right there. That means that when you sweep over 3 pi over 2, you're facing 3 pi over 2, you're going to also go up 1, right? You're going to go up 1. The same way how when we're facing pi over 2, this angle, we're going up 1 as well. So we have 2 points right here. Now, I want to know what happens in these angles between. Right, so I want to see what's happening from right here, from 0 all the way to pi over 2, and I want to know what's happening over here as well. Right, but it doesn't mean that you have to graph every single angle possible, right? You don't have to graph all these, or you'll take forever. You get a really accurate graph, but you don't have to do that. Instead, what I found is better is to just try to graph these angles first and see if you can determine a sort of pattern or some symmetry going on. So let's try pi over 6. When you plug in pi over 6, we get r equals 1 plus cosine of pi over 6. The cosine of pi over 6 is radical 3 over 2. So this is 1 plus radical 3 over 2. Now, I know that radical 3 over 2 is roughly 0.87, but you don't have to know that. All you have to know is that it's bigger than radical 2 over 2, and radical 2 over 2 is bigger than 1/2. So it's definitely not 0.5, and it's a little bigger. It's bigger than radical 2 over 2, which is already bigger than 0.5. So it's somewhere around there. You don't have to be super precise. Just know where it kind of lies, right? But it is useful to know that it is closer to 0.87. So this is going to be 1 plus 0.87. So you have 1.87. This is going to be 1 point, sorry, not 1.7. Not 1.7. This is going to give you 1.87. So when we plug that in, right, that means that when we're facing pi over 6, this angle right here, we're going not to 2, but a little closer to. So we're going to 1.87, which is like about right here, right? Because if this is our 1, this is our 2, we're kind of like right there. So we can just plot a point right here. Let's try pi over 4 now. at pi over 4, we have r equals 1 plus cosine of pi over 4, which is 1 plus radical 2 over 2. Now, again, remember, radical 2 over 2 is not as big as 0.87. It's not as big as radical 3 over 2, but it's bigger than 1/2. So as long as you're in between those two, right, in between 0.5 and 0.87, then you're fine. But again, if you want to be really accurate, it is, radical 2 over 2 is approximately 0.71. So this is 1 plus 0.71. So we get 1.71. Now, if we look at our graph, that means that when we're facing pi over 4, this angle, we go up to 1.71, which is less than what we just put, which is 1.87 right here. So it's going to be somewhere around right here, right? So now we can plug in right here. You can kind of see a little trend happening, right? You see how it's kind of getting smaller, but then it's reaching that 1 on the left. So instead of actually plugging, just doing pi over 3, I want to now know what are the inflection points, right? So the inflection points are going to be the points where 3 cosine theta and 1 plus cosine theta meet, right? I want to see where both these graphs are going to have intersections. And this is going to actually tell us what our bounds are when we do our the actual calc part. So to find the inflection points, we're going to plug in 3 cosine theta, which is our first graph, and we're going to equals that to the other graph, 1 plus cosine theta. And we're going to solve for theta. This is going to tell us exactly where they meet. So we can do minus cosine theta. We get 2 cosine theta is equal to 1. Divide by 2. You get cosine theta is equal to 1/2. Now to find theta, we do theta is equal to the cosine inverse of 1/2. So at what angle are we going to get 1/2 for cosine? So we have to find these angles. So you know that in the first quadrant, cosine is 1/2 at pi over 3, right? Because at pi over 3 from the unit circle, this gives us 1/2 and radical 3 over 2 right here, right? So we know that one of these angles is going to be pi over 3. Now, what's the other angle? Well, we know that the only other angle where cosine is positive is down here in the fourth quadrant. So you have to go pi over 3, but just down to the fourth quadrant. So just right here. What's that angle? All you have to do is get 2 pi and subtract your angle that you want, pi over 3. This is equivalent to saying 6 pi over 3 minus pi over 3. So we get 5 pi over 3. So at pi over 3 and at 5 pi over 3, we get a cosine of, or our cosine is equal to 1/2. So these are going to be our inflection points. Right, so these are the points where both of our graphs are going to end up meeting. So now what we can try to do is, let's just plug in both of those and see what we get there. So if we do pi over 3, and we're going to do 5 pi over 3 as well. So we're going to do r equals 1 plus cosine of pi over 3. 1 plus, and then the cosine of pi over 3, as we just said, is 1/2. So we get 1.5. And then when we do the other one, r equals 1 plus cosine of 5 pi over 3, we get also 1 plus 1/2, which is 1.5, because remember 5 pi over 3, cosine of pi over 3 and cosine of 5 pi over 3 give you the same thing, they give you 1/2, just in different quadrants. So you have 1.5 for both of these angles. So we can graph this now. So we know that at pi over 3, we're going to hit 1.5. Now, yes, this isn't exactly to scale anymore, right? It's a little weird, but again, it doesn't matter. It doesn't have to be perfect. We just know that it's kind of going down, right? It's sweeping down when you're going like this, right? It's kind of like going less and less. And then it's reaching the 1 right here. And now we know that when you go down at pi over 3, but going down instead of going up, so we know that that's 5 pi over 3, which is like right here, 5 pi over 3. We know that it also reaches 1.5. It's the same as this one we just had. So it's going to just be that, but right here. So there's this, you can see that there's some symmetry going on. We can assume now that this right here reaches like that, right? Something like this. And that it's going to, the same thing's going to happen going this way, right? Just because we can see the symmetry that's going on. You can test it out. You can graph more things. You can graph these angles, right? You can graph pi over 4 going this way and pi over 6 going this way. Again, if you want to find exactly what those angles are, you get 2 pi and subtract it by those angles. So 2 pi minus, say, pi over 6, that's 12 pi over 6 minus pi over 6, you get 11 pi over 6 right here. 2 pi minus pi over 4 is 8 pi over 4 minus pi over 4, you get 7 pi over 4. Now you can try these points and plug them in and then find their values, and they're going to be the exact same as these counterparts that you got right here. It's going to give you the exact same thing. They're going to be symmetrical. All right, so you don't actually have to do that work if you recognize that there's some symmetry going on. Now, let's see. I want to know what happens. We don't know what happens over here. We do know, though, that at pi, when it reaches pi, it goes back to 0. But we don't know exactly what's happening in between. We don't know if it's looking like this or like this. Right? It could be like this. It could be like this. Or it can go straight down to nothing. It could be huge and then go back. We don't know. So let's see by just getting a random angle in between right here, right? In between pi over 2 going this way and in between pi, which is facing that way. Right? Remember, at pi over 2, right? We land at pi over 2 and we're facing that way. Once we land at pi right here, we're facing that way. We don't know what's happening over here, right? So let's just pick something in the middle. Let's pick pi over 4, but in the second quadrant. So this would be like right here. This would be pi over 4 in this quadrant. Now, what is that, right? It's just pi minus pi over 4. So that's going to be 4 pi over 4 minus pi over 4. So we get 3 pi over 4 right here. So let's see what happens to 3 pi over 4. So we plug in 3 pi over 4, we get r equals 1 plus cosine of 3 pi over 4. Now, what's the cosine of 3 pi over 4? It's the same as cosine of pi over 4, which is radical 2 over 2, or 0.71. Except, since it's in the second quadrant right here, you see that cosine is negative right here. So we know that it's going to be the same thing, but just negative. So this is going to be 1 minus radical 2 over 2, or 1 minus 0.71, which is 0.29. So we know that 3 pi over 4, we get 0.29. So now we know that that's 0.29 right there. We know that when we sweep along, so again, when we swept along to pi over 2, we found all these angles and with these points. When we swept along to pi over 2, you see we got 1, right? So we know it's 1 right here. We don't know what's happening here. We don't know what's happening here in the middle right here. But we know now that at 3 pi over 4, so when you're facing 3 pi over 4, we know we just got 0.29. So it's barely going to go right here, right? Barely. So we can draw a point like right here. Okay? So we know that somehow this is going to connect like this. It's going to get to here. And then at pi, remember at pi going this way, that we have 0, right? That's what we got, pi, 0. So we know that it's going to go like this. It's going to connect it right here. And then it's dipping back to 0, like that. So we can draw kind of like this little dip right here. Now, again, from our symmetry, you can do it again, and you can get an angle right here, right? You can get that. This would be 5 pi over 4. You can go ahead and do that, but you're going to get the same exact thing. So it's going to be like right there some point. So you can just connect it, kind of just make it symmetrical. And you see that we kind of made a little heart. This little heart in polar graphs is called cardioid. So we just found out that this graph is just a cardioid. And we also found our inflection points already, right? From when we were doing this, it was pi over 3, 5 pi over 3. These are our inflection points. So this means that it meets, these graphs meet right here at pi over 3. So remember, again, like I drew the pi over 3 right here, which wasn't too accurate, right? It should have been like more right here. It doesn't matter. We found it mathematically already that these are the inflection points right here. Our pi over 3, right? Our pi over 3 and our 5 pi over 3. And now the question says find the area of the region that lies inside the first curve and outside the second curve. Inside the first curve, right? That's our first curve is 3 cosine theta, which is our circle. Inside of there is right here, this whole thing inside. But it says outside of the second curve. So outside of the cardioid is outside of this, and inside of this is this little part right here. This is the area we're trying to find. So we want to find this area, right? And bounded by those two inflection points. So now we're going to use the formula to find the area between two polar curves. Now this formula is going to be 1/2 of, or 1/2 times the integral of alpha to beta, right? These are polar bounds. And we're going to have f of theta squared minus g of theta squared d theta. Now, f of theta, this is our outside curve, and g of theta is our inside curve. So what's our outside curve? Our outside curve is a circle. You see, that's on the outside of our area. So our outside of our area is our circle, which was 3 cosine theta. So we're going to have 1/2 of 3 cosine theta squared minus, and then our inside curve was 1 plus cosine theta. 1 plus cosine theta squared d theta. What's our bounds? Well, our bounds, remember, we're starting from here to there, right? This is, we're getting this area, right? Remember, because when you're doing polar graphs, you're kind of doing it like in a sweeping way, right? You're sweeping, and we're sweeping from this angle to all the way to here, to that angle, because that's where our inflection points are. So we're going to go from 5 pi over 3 to pi over 3. So from 5 pi over 3 to pi over 3. Now, I don't really like 5 pi over 3. I don't want to plug 5 pi over 3 in. So something we can do is that you can look at it and realize that there's some symmetry going on. Starting from right here, you see how we have this like little half moon, right? Have a little shape. It's the same as this one, right? These are the same. So we can actually just choose to start at 0, right? This is angle 0 facing that way. We can start here and choose to go from here, sweep all the way to just this inflection point, and just get this area, right? From these angles, from 0 to pi over 3. And just make sure we multiply by 2 so that we get both of these. Okay, so I'm going to change that angle from, and get rid of that 5 pi over 3. I'll do 0 to pi over 3. Multiply that 1/2 by 2. This gets rid of it. And we're going to now distribute that. And now we square everything. We get 9 cosine squared theta minus, and then we get 1 plus 2 cosine theta plus cosine squared theta d theta. And now it's just a matter of working out this integral, which is 9 cosine squared theta minus 1 minus 2 cosine theta minus cosine squared theta d theta. Now we get 0 to pi over 3 of 8 cosine squared theta minus 1 minus 2 cosine theta d theta. Now what I like to do in this situation is split the integrals. Now you don't have to do this. There's a lot of ways to integrate this, but I'm just going to do 0 to pi over 3 of 8 cosine squared theta d theta. Right, that's our first integral. Minus the integral 0 to pi over 3 of 1 d theta minus 2 times the integral of from 0 to pi over 3 of cosine theta d theta. And that's all our integrals just separated because you can separate integrals by term. So let me evaluate this first integral on the left. So if we evaluate that first integral on the left, we get 8 times 0 to pi over 3. I'm going to reduce the power of cosine squared using the half angle identity. It's going to be 1/2 times 1 plus cosine 2 theta d theta. If we take out the 1/2, we get a 4 on the outside, and we have 0 to pi over 3. And now we're just integrating 1 plus cosine 2 theta d theta. So at the end, we get 4 times, and then this is theta, plus 1/2 of sine 2 theta. Now distributing that forward, we get 4 theta plus 2 sine 2 theta. Next integral, this is just negative theta. That one's easy. Third integral, we get negative 2 times the sine of theta. So that's all our integrals. Now I'm going to bring all of them together and evaluate them all at once. So I'm going to bring all those together. So we have 4 theta. Actually, since we have that 4 theta and then that minus theta right here, so we actually just have 3 theta. I just combine those right away. 3 theta plus 2 sine 2 theta minus 2 sine of theta. And this is evaluated from 0 to pi over 3. 0 to pi over 3. So we can just plug all those in. So we get 3 times pi over 3 plus 2 sine of 2 times pi over 3 minus 2 sine of pi over 3 minus, and now this is just 3 times 0, so that's 0, plus 2 sine of 2 times 0, well, sine of 0 is 0, so that's 0, and then minus 2 times sine of 0, again, sine of 0 is 0, so this whole part is 0. So really just worry about this left part. These 3's cancel out. We get pi plus 2 sine of 2 pi over 3. Sine of 2 pi over 3, well, what's sine of pi over 3? The sine of pi over 3 is radical 3 over 2. The sine of 2 pi over 3 is the same thing in the second quadrant, but sine is also positive in the second quadrant. So it's going to be the same thing. It's going to be radical 3 over 2. So 2 times radical 3 over 2. Then we have minus 2 times sine of pi over 3. The sine of pi over 3 again is radical 3 over 2. So now these 2's cancel out. And now look, we're left with radical 3 minus radical 3. So these go away. We're left with, the answer is just pi. And that's our answer.